The teacher assigns 10 minutes of detention for each tardy, but subtracts 2 minutes each time the student is not tardy. How many minutes of detention would you expect? Here's a key word here. Would you expect the student to serve in a 180-day school year? So this is an expected value problem. The expected value can be calculated by multiplying the probability of an event by the value of an event, and then adding to that the probability of a second event multiplied by the value of that second event. And you keep going until you've accounted for all the events. This first event, the probability of being tardy is 1/5. And when you are tardy, the teacher assigns 10 minutes of detention. To that, we'll add the probability of not being tardy. If there's a 1/5 probability of being tardy, there must be a 4/5 probability of not being tardy. Those are complementary events. Either one or the other must happen, but they cannot happen at the same time. So they add up to, those two probabilities add up to 1. So there's a 4/5 probability of not being tardy, and when that occurs, the teacher subtracts 2 minutes from the detention time. So we'll represent that with a -2. Here we have 10/5 plus -8/5. 10/5 plus -8/5 is +2/5. So the expected value for a single day is 2/5. There's a 180-day. Actually, I'm going to pause for a second and try to interpret that. I'm a bit confused because, no, that makes sense, because if there was 10 minutes for the week, that would average out to 2 minutes per day, but you get back all those 8 minutes, which should also be averaged out. Okay, so that at first this answer didn't seem reasonable to me, but the more I think about it, if you multiply 2/5 times 5, that's 2. So on a typical 5-day, if a 5-day school week is typical, then you multiply 2/5 by 5, you get 2 minutes. If the student has a 1/5 probability of being tardy, let's just say 1 out of 5 days they're tardy. So let's say they're tardy on Monday, so there's 10 minutes of detention. But you subtract 2 minutes from Tuesday, Wednesday, Thursday, Friday. So 10 minus 8 is 2. And that 2 minutes of detention has to be divided by 5 to average it out to the number of minutes per day that you end up serving. So that this is reasonable. At first I didn't think it was. But this is the expected value for detention minutes served per day. There's a 180-day school year, so we need to multiply 2/5 by that 180. That's 360 divided by 5. I know 300/5 is 60, and 60/5 is 12, so that's 60 and 12, 72. That student would expect to serve 72 minutes of detention in an average 180-day school year. Problem number 10. We want to compare the probability of flipping 3 coins and having them all land on tails to the probability of rolling 2 standard dice, that's a die with 1, 2, 3, 4, 5, and 6 on its faces, and having them both land on a number greater than 4. The probability of flipping a coin and having it land on tails is 1/2, so the probability of getting tails, tails, tails is equal to the probability of tails multiplied by probability of tails multiplied by probability of tails. Or 1/2 multiplied by 1/2 multiplied by 1/2. That's 1/8. The probability of rolling 2 standard dice and having them both land on a number greater than 4, we'll represent that as probability greater than 4, greater than 4. That's equal to the probability of greater than 4 multiplied by the probability greater than 4. Greater than 4 does not include 4. 4 is not greater than 4. 4 is equal to 4. So the two favorable outcomes are the 5 and the 6. So we have 2 favorable outcomes out of 6 possible outcomes, multiplied by, again, 2/6. Those are independent events. Each of these simplifies to a third, so we get 1/9. 1/8 is greater than 1/9, so A is greater than B. Problem number 11 is an SAT from an SAT test preparation resource. It says a bag contains 3 red marbles and 6 black marbles. What is the probability that you select 2 red marbles if you reach in the bag and randomly grab 2 marbles without replacement? Now, based on the work we've done, I wouldn't have even included the words without replacement here, because we've talked about the fact that if you grab 2 marbles at a time, those are dependent events, and that's hard to wrap your head around that. We had a discussion about it. It's hard for me to really understand it too. I have to think about it like, even if I grab them at the exact same time, there's no such thing as the exact same time. I'm grabbing one before the other, and so the first one I grab is not available to grab when I grab the second one. So if you just realize that, but the words without replacement here make it very clear that these are dependent events. So I want probability of red and then red after red. That's equal to the probability of red multiplied by the probability of red after red. The probability of red is pretty straightforward. There are 9 marbles total and 3 of them are red, so that's a 3/9 probability. The probability of selecting a red marble after selecting that first red marble, there were 3 red marbles, now there are 2 red marbles. And there were 9 total marbles, now there are 8 total marbles. This 3/9 simplifies to a third, 2/8 simplifies to a fourth, and so our product and our probability is 1/12. Problem number 12, a pair of dice is rolled. The smaller number is subtracted from the larger to determine the difference. If doubles are rolled, the difference is 0. What is the probability that the difference rolled will be greater than 3? You can do a tree diagram here. I wouldn't recommend it, so I'm just going to show you why I wouldn't recommend it first. If I roll a 1 on the first die, I can roll a 1, 2, 3, 4, 5, or 6 on the second die, and I can start finding these differences. This is a difference of 0. The smaller number is subtracted from the larger, so this is a difference of 1, 2, 3, 4, 5. You could do it this way and consider all the differences, but because we have 6 possible outcomes for each die, it makes a nice square array if you show the sample space on a grid. And so we've done a little bit of that, but I'll show you what I mean by that again here. There are 6, so I'm going to try to split the difference here as best I can. And then figure out that there's 3 here, so I'll just sort of eyeball this and try to make this. It doesn't have to be perfect. You're doing yours by hand, so as long as you can fit in all the numbers, that's all that really matters. So I have the possible outcomes here are 1, 2, 3, 4, 5, and 6 on the first die. On the second die, I also have 6 possible outcomes. One, 2, 3, 4, 5, and 6. I'm going to place the difference in each of these boxes. If I roll a 1 and a 1, the difference is 0. If I roll a 1 and a 2, the difference is 1. A 3 and a 1, the difference is 2. A 4 and a 1, the difference is 3. A 5 and a 1, the difference is 4. If I roll 6 and 1, that's a difference of 5. If I roll a 2 and a 1, that's a difference of 1. 2 and a 2, that's a difference of 0. If you keep filling in this table or this grid, you'll see a pattern. All of the doubles result in a difference of 0. Everything down this diagonal has a difference of 1. as does everything down this diagonal. It's a little different than when we did the sums of the two numbers. Everything down this diagonal will be a difference of 2. Same here, differences of 2. Difference of 3 down this, oops, not there. Down this diagonal and this diagonal. Get a difference of 4 on these two, difference of 4 on these two, and a difference of 5 in these corners. The probability that the difference rolled will be greater than 3, we'll go to the definition of probability. It's the favorable outcomes over the total possible outcomes. The favorable outcomes will be the differences that are greater than 3. That does not include 3. Greater than 3 would be the 4s and the 5s, and I count 3 of them there and 3 of them here. So there are 6 favorable outcomes out of a total of 36 possible outcomes. That simplifies to 1/6. A 1/6 probability of rolling a difference greater than 3. Okay, I hope that helped. We'll pick up the review with page 4 on the last